Okay, thank you. Thank you very much for the introduction, and thank you all for coming to this session on quantum computation. My name is Robin, and I'm here to spread the good word about quantum information effects. But before I can do that, I'd like to talk to you a little bit about the cost of computation, in fact, to motivate this. Because the cost of computation is something that, as computer scientists, we're trained to do sort of like from a very early stage, and something that happens like almost automatically for us. And the way that we typically analyze the cost of computation are in terms of time and space, like how long does it take to run this algorithm, and how hungry is it for memory, so on, right? But of course, these are not the only costs involved in doing computation, and one of the costs that is often left out is information cost. But what does that even mean? Well, let me illustrate by some examples. So let's consider the following two functions on 32-bit integers. So we have one that takes an integer and increments it by 1. And let's just say that this is modular arithmetic. So if the result would go out of bounds, we just sort of loop around. And the other, which takes a 32-bit integer, and no matter what it is, just returns 0. Now, what is the information cost of these two functions? Well, I mean, if we apply inc, this is free, right? No information is actually lost in this transaction, right? Because we can always recover the input from the output, right? So no information is actually lost here. It's just sort of been slightly transformed, but we can get it back if we really want to. On the other hand, if we apply reset, then that actually costs us 32 bits of information, because no matter what we give it, it returns 0, right? So whatever information we give it, that is now lost to the ether. Now, interestingly, we can't really see this in the type signatures, though. They have the same type signature. But what if we actually wanted this? So to actually, let's say, fix this problem, some very clever guys, Risham James and Amar Sabri, wrote a paper about this 10 years ago, in which they showed that classical computation can actually be explained through two things, through classical reversible computation and information effects. So classical reversible computation is significant because reversible computations all have information cost 0, right? Reversible computations can be undone. So if I can do something in the forward direction, I can always undo it, right? So what's left really of classical computation are these information effects, which are effects that sort of, let's say, explicitly alter the amount of information that's there. And they identify two of these. There's one which erases information and one which creates information. Now, the reason why we call these information effects is because they were able to actually show that this fit quite neatly in a framework for effects called arrows. So actually, we could see this as sort of a very clever arrow construction on top of a reversible programming language. So then we wonder, of course, since quantum computation is actually usually presented as being reversible, is there an analogous result for the quantum case? But to actually answer this question, we'll need to turn to, we'll need to be able to actually analyze like quantum information costs, right? But to do that, we'll first need some bit of background on sort of the quantum mixed state formalism. Now, yesterday at the keynote, Professor Aho discussed the quantum pure state formalism. And this is the one that's usually used when we talk about reversible quantum computation. But if we actually want to talk about measurement, specifically measurement outcomes, as having that being a part of theory, we'll need to go from pure states to mixed states. So with the mixed state formalism, we still have the same classical states and quantum states as we had before, but we also have a third kind of state, which are these probabilistic mixed states. And what they are well, as it sort of suggests, they're like probabilistic states. So like with some probability, it's this state. With this probability, it's the other state. So for example, I've given you two examples here. So one is with probability 1/4, this is the classical state 0, and with probability 3/4, this is the classical state 1. The other one is sort of a 50-50 one instead. And then you'll notice here that instead of in the pure state formalism representing this as vectors in a 2 to the n dimensional vector space, we now represent them as certain kinds of matrices here, 2 to the n by 2 to the n matrices, where n is the number of qubits in your system. Now, this allows us to actually talk about measurement as something happening inside the system. Now, there's a lot of debate going on, mostly by physicists, about what measurement actually is what is the nature of that, and so on. And there's this wave function. Does this just collapse? What's going on with that? I'm not going to spend like too much time on that side of things, but I will just say that there is most definitely, no matter how it happens, this observer effect, where if we observe or measure a quantum state, then when we do that, it decays to a probabilistic classical state. And I've illustrated precisely how that happens down here in the case of 1-qubit systems. So, okay. So let's talk about quantum information costs. So here we have two quantum functions. So one is, it's basically a quantum knot. So it's the usual Boolean knot, and it does precisely that, but it operates now on qubits instead of regular bits. So that's the first one. And the second one is this measurement, which takes a qubit and then measures it. And then we can ask again, okay, what is the information cost of these two functions? And well, applying the knot function again is free, right? Because we can always recover the output just by applying it again, in fact, or recover the input, I should say. On the other hand, whenever I apply measure, I spend my qubit in a sense, right? Because what measure does is that it decays my quantum, or the state of my qubit, into actually a classical state now, a classical probabilistic state. So I lose all of my quantum correlations. So in fact, what we'll see here is that the observer effect destroys quantum information. So what does this have to do with quantum information effects? So all of a sudden, this seems to be something about measurement. So what James and Sabri did was that, well, they're basically able to show that classical computation is reversible computation with these information effects for allocating and erasing information. So the question is, can we make sense of quantum measurement and the observer effect by sort of similar means? And of course, to this, there are some follow-up questions like, okay, does that mean that the observer effect is actually a computational effect? And does it mean that pure states are actually computationally pure? And to sum up, yes, we can, and yes, they are. Okay, and here's how. So here's what we did. So we introduced a quantum programming language called Yuppie, right, which is actually based on James and Sabri's classical language, Pi. I'll get back to how that looks in a moment. Then we will successively extend that with two information effects. First one for allocating information, gives us the language Yuppie-A. And then we'll extend that further with the notion of hiding information, which gives us the language Yuppie-Chi-A. And then finally, we'll argue that actually in Yuppie-Chi-A, we can account for quantum measurement. Okay, so let's do that. So first of all, what is Yuppie? Well, outside of that, what is Yuppie? Well, let's talk about Pi first for a second. So Pi is a very simple, almost boring, finite reversible programming language based on simple first-order combinators on linear products and linear sum types. Okay, and basically, if you can, read their names and their type signatures, you know what they do because they do exactly what you think they do. Okay, and once we have these primitive combinators, we can combine them in different ways. We can compose them either in sequence or in parallel using either plus or times. Now, the most, I guess, surprising thing about this language is actually that it's already universal for finite reversible classical computation. So it's a good starting point for us. So what do I actually need to add to make this quantum? Well, it turns out not too much actually. So here we extend this to Yuppie by adding two distinctly quantum combinators. So one is kind of phase combinator. If you don't know what a phase is, don't worry about it. It's kind of like a quantum unit. And the other one is this Hadamard combinator, which Professor Aho also talked about yesterday, and it's pretty much a way of introducing and eliminating quantum superpositions. Now, these two, along with all of the operators that we had, or combinators that we had before in pi, are actually unitaries, which are these reversible quantum computations. So then, we can wonder if we actually have enough of these, and it turns out that we do, in the sense that Yuppie is what we call approximately universal for unitaries acting on qubits, and that's pretty much as good as we could get. Okay, so that was the base language done. Now we need to add these two effects. So how do we do that? Well, let's start with allocation, because the idea is that on top of this base language, we'll add first an effect for allocation and then one for hiding. But they'll turn out to be very similar, actually. And the idea is that we will build this new language, Yuppie, on top of Yuppie by basically letting Yuppie combinators be given by Yuppie combinators, but with like a bit of like extra input, which we think of as a kind of like a hidden heap that we can allocate from. So a Yuppie combinator from, say, B1 to B2 is just given actually by a Yuppie combinator, but here from B1 plus B3. So with this extra bit of input and into B2. And from this, we can actually implement something like allocation, as it's done down here. And actually, just like in James and Sabri's case, this actually extends to an arrow with choice over Yuppie. In other words, we can define things like pure arrows or R, and arrow composition, first, left, and so on. Now, when we have that, we can actually use this allocation combinator and the other ones to further define a classical cloning combinator. So one that takes B to something B times B. Now, before you complain, no, this does not violate no cloning, okay? Because if you give it a quantum state, this does not, in fact, give you two copies of it. It'll do something a bit different. But again, what these are all isometries, which are like roughly the sort of injective quantum computations. And there are, in the sense, enough of them in the sense that this language is approximately universal for isometries acting on qubits. So far, so good. But then, how do we do this hiding? So what this Yuppie, what's that about? Well, Yuppie, I'm not going to say it. I'm not going to say it. You imagine it. Okay. Aside from that, what is Yuppie? So it's Yuppie with hiding and allocation. So the way that we perform hiding is basically we do exactly what we did before, but we dualize everything. So we think of a combinator in Yuppie from, say, B1 to B2 as being given by a combinator in YPA with a bit of extra input, which we think of as like a hidden garbage dump that we can put all the stuff that we don't care about. So if we want to throw something away, I can just put it there, and then it's sort of safely out of view. And again, this allows us to implement like a discarding combinator, and in turn, it extends actually to an error with choice. So indeed, this is a kind of effect over YPA and in turn over YP. So again, using discard and using these other combinators, we can derive things like projections, but also measurement. And we'll get back to how that looks in just a second. Now, I just want to get this expressivity theorem out of the way, because again, we noticed that these are actually all quantum channels, which are sort of like the arbitrary quantum computations that you can perform on mixed states. They're also known as CPTB maps. And again, we can show that actually YPKIA is approximately universal for these. So, but how does this measurement then actually work? Well, if you're sort of classically inclined, I mean, this looks completely insane, right? Measurement is you clone and then you throw away one copy. That seems insane. That doesn't do anything, right? And you're right, classically, it doesn't do anything. But then again, measurement of a classical state isn't supposed to do anything either, right? But what it actually does is that it aligns quite nicely with the explanation of measurement offered by decoherence, which is the idea that what we're seeing as the observer effect is actually a result of sort of quantum information leaking into the environment. And so the idea is that, well, how does that happen? Well, what clone actually does is that it sort of prepares a new qubit, and then on top of that, it applies some reversible operations to sort of perfectly entangle the qubit that we started with this new one that we prepared. And then when we apply first, we forget one half of this system. We throw that away. What does that mean? Well, it means that this thing, right, is now no longer considered part of my system. It's now considered part of the environment. So what we have essentially done is that we have devised, precisely a process of leaking information into the environment, right? Decoherence. The point being that, well, in this sense, no actual wave function collapse occurs. It just appears so from the inside. So in conclusion, with quantum information effects, we can give a type level separation between quantum programs which measure their inputs and ones which do not. And we can actually also give an account of measurement and decoherence through these two quantum information effects of allocation and hiding. And it does indeed turn out to be the case, in this framework, that the observer effect is computational effect and that pure states are computationally pure. So if nothing else, this is like a very pleasing confluence of terminology from physics and computation. Now, there's a bunch of things that I didn't mention in this talk, but which, if you think are interesting, you can look at in the paper. So all of this is based on a categorical semantics based on universal constructions applied to grid categories. So if that sounds interesting to you, read the paper. We also give a purely categorical statement of Toffoli's fundamental theorem of reversible computation. We show how you can use this framework for actually reasoning about measurement without using Hilbert spaces, just use grid categories instead. And finally, we also give an interpretation of some quantum gate sets and quantum flowcharts without iteration. So yeah, read the paper. We also have an artifact if you want to play around with that. And if you have more questions, I'll be happy to take them here, or please schedule an appointment with me. Send me an email, book me a Zoom meeting, and yeah, I think that's it. That's it for me. Thanks.
All right, let's thank the speaker. So I'm going to take the first question remotely. Robin, can you hear me?
Yes, very faintly.
So the first question is from Eric Bond, who's a senior research scientist at 26 Technologies. And he wonders if you can elaborate on approximately universal. What does that mean exactly?
Right, great question. Yeah, so okay, so let's go back. So why is approximately universal actually necessary? So it turns out, when we're doing classical computation, we're used to having, okay, say, this gate or whatever is universal, which means that, any, classical computation can be expressed in terms of just that thing or things from that gate set or whatever. The problem with that in the quantum case is that since everything is sort of over the complex numbers, you'll actually need like an infinite amount of different gates to actually be universal. So then we say, okay, like what if we don't need, say, like an infinite gate set? Can we do something about that? And it turns out that, well, if you're happy to accept a small error, and in fact, you can choose that error. So let's say that you're happy to implement not just the unitary you give me, but unitary that's very close to it, up to some error that you give me, and you can do that for any unitary. Then the result is approximately universal. Does that answer your question?
Well, thank you for your answer. Are there any questions in the room? Okay, so I'll do another question that's remote.
Yeah, go ahead.
Okay, so the question is from Kartik Singhal from University of Chicago. Your measurement construction sounded like purification by expanding the considered Hilbert space. Is that an accurate thinking about it?
Absolutely. So really, that's this decoherence point of view of measurement, right? That actually well, what we're doing, when we're measuring things, is really that we're sort of saying, okay, there is this part of the environment that I'm entangled to. I'm just going to forget about that. And in fact, you can express purification in this setting, and it's actually in the paper, but it's not expressed in that way because I just realized that like yesterday. But there is this factorization theorem, and what that factorization theorem in the paper basically amounts to is purification. So yeah, extremely good question. Thank you.
Okay, thanks. So there is one more question in the chat, but I'm going to invite you, Robin, to just answer it in the chat so that we can move on to the next speaker. So everyone, again, let's thank Robin for his talk.
Thank you.